this lecture, we are going to discuss the viscosity of solutions and mixtures. And also we will outline the methods available in the literature for the estimation of the viscosity of solutions and mixtures. So first of all, what is viscosity? Viscosity is actually a measure of the solution's resistance to the deformation at a given rate. For liquids, an informal concept of thickness is used, like we said that the honey is thicker than water. Viscosity can be conceptualized as quantifying the internal frictional force that arises between the adjacent layer of fluid that are in relative motion. So here we have an example of a tube in which a liquid is flowing towards this direction. So here we have several layers of the liquid. So for instance, when a liquid or fluid is forced through a tube, it flows more quickly near the tube's axis than its walls. So according to this diagram, the fluid is flowing more easily towards right and in horizontal direction, whereas in the perpendicular direction or towards the walls of the tube, its flow is minimum. In such case, some stress such as pressure difference between the two ends of the tube is needed to sustain the flow through the tube. So it means that there should be a pressure difference between the two ends of the tube so that this fluid can continue to pass through this tube. So this is because a force is required to overcome the friction between the layers of the fluid which are in relative motion. The strength of this force is proportional to the viscosity. So here the smaller arrows are showing the direction of frictional force as compared to the horizontal vectors, which are showing the flow of or the dimension of the liquid. So here we need to keep in mind few points. For example, a fluid that has no resistance to shear is known as an ideal or inviscid fluid. Here this word describes the smooth flow of the liquid or the relative motion of the two layers or different layers of the fluid. Another point is zero viscosity is observed at only very low temperatures in the superfluids, and according to the second law of thermodynamics, all liquids must exhibit positive viscosity. It means that all fluids have some value of viscosity as they are behaving as non-ideal fluids. So the solution or the fluid or the liquid exhibiting a specific positive value of viscosity are known as viscous or viscid fluids. Viscosities of the solution and mixtures are very important at the industrial scale because they are needed to design the different unit operations. Here we have two terms known as solution and the mixture. The word solution is usually referred to the mixture of solids or gases in the liquids, whereas the mixtures are commonly referred to a mixture of liquids only. We have few methods which are available in literature for the estimation of viscosity, which are outlined here, in which first one is Falcon Hagen relation. So this is the theoretical equation that is applicable for the determination of the viscosity of dilute as well as concentrated electrolyte solutions. So for the dilute solution, the relationship is expressed as equation number 1. So here this is the symbol used for the viscosity, and S represent the viscosity of the solution, whereas this one is viscosity of solvent, and here C is the concentration of the solute, and A is a constant that have non-zero value, and it depends on the electrostatic forces between the ions of the solute particles. And this equation fit well for the dilute solutions. The second equation is given by Jones and Dole, is known as John-Dole equation. So John and Dole also proposed a similar equation as proposed by Falcon-Hagen theory, and this equation enables the calculation of constant A for the case of equal ionic valencies. For example, for the case of sodium chloride, Z1 would be for sodium and Z2 would be for chlorine, and for both equivalent ionic valencies that is equal to 1 for both cases, and equal ionic mobilities by following equations. So here we have the equation number 2, in which the constant A is equal to this term, in which this epsilon is the dielectric constant of the solvent, viscosity of the solvent, absolute temperature, valency of the equivalent ions of the solute, and this factor or parameter is known as ionic mobility at infinite dilution. So ionic mobility for the equal ionic valencies, or that is expressed in terms of ionic velocity with respect to potential gradient. It is actually the movement of charged particles in response to an electric field. So the units of the ionic mobility is centimeter square per volt per second. So this equation holds good for the equal ionic mobility of the two ions, like for sodium chloride, the ionic mobility of sodium ion and chloride ion must be equal, that is equal to the mobility at infinite dilution. So here we can say that the values of A calculated from the above equation, this one, are found to agree closely with the values calculated from the viscosity data that is determined experimentally. The theoretical treatment has been extended by Onsager and Foss to include the viscosities of the solutions containing any number of ionic species. So for more concentrated solution, equation 1 become equation number 3. Here another factor B with constant B and the concentration C is added. This expression is also given by the John-Dole. We will discuss the Onsager-Foss equation in the next lecture. So in equation number 3, B is also a constant which depends on the interaction between the ions and molecules of the solvent. For higher concentration up to 1 mole per liter, a 3 constant equation is used that is similar to the equation number 3 and the equation number 1, with additional constant known as C, and the product of concentration with factor of raised to power 2. So here we have some our constants A, B and C for the few examples of aqueous solution, like for sodium chloride, potassium iodide and potassium sulfate. So the above equations are applicable not only to the solution of the electrolytes in water but also solutions of electrolytes in non-aqueous solvents like methanol, ethanol or nitrobenzene. In next lecture we will discuss about the Onsager-Foss equation and the viscosity of mixtures.